Okay, in the last video, we were talking about molecular forces, which is the glue that begins to hold these molecules and atoms together, whatever that means. All right, so we're talking about glue, and I'm not talking about this kind of glue. I probably have sniffed a little bit too much of this glue when I was younger, which is why I'm a little bit cray-cray today. But this is kind of the idea of what's going on with molecules. So molecules stay together for a reason, and that's because the atoms that make them up come together and they hang out with each other and they're okay with each other and they just get along and they have a great time and they never want to come back home, and before you know it, they've broken their curfew and now they're grounded for the rest of the week. So we need to talk about more with glue. Now, again, not Elmer's glue, but the chemical kind of glue that keeps the stuff together. Because it's this stuff, ladies and gentlemen, it's this stuff. These molecules have this glue that we have to overcome when we do some of these physical property tests in a laboratory environment. So with that said, I kind of want to take you back to the basics. I'm going to take you back to the basics of a general chemistry class. And I know you probably have hated one of those courses in the past, but that's okay because I'm going to get ready to give it to you a little bit better, I hope at least, than what you got it the first time through. Especially if you've taken like a chemistry 151 or a chemistry 131 or a high school chemistry class or whatever it is study that you've taken, I don't know, but either way, I'm going to break it down, hopefully, a little bit simpler for you. All right, so first off, we're going to start with something called the atom. Oh, how sweet. All right, so what I want you to think of, imagine that you've got a microscope, and that microscope is zooming in and in and in and in and in and in and in, and you're getting smaller, as far as you can go. And we are down to the atomic level. All right. I want you to think of like Ant-Man off of Marvel. Okay. So we are down at the atomic level. And when we get at the atomic level, there's something called an atom. And the atom is basically the building blocks, is really how we like to describe this. The building blocks of everything. I mean, everything. The water that you drink, the brain in your head, I hope you've got one, and then all of the chemical reactions that go on inside of your body to make you see and to make you think and to make you talk and to make you breathe. Everything that you've come in contact with, the maybe pen or pencil that you're holding in your hand, the notebook paper that you're writing on, all of those are made up of atoms. Those are the building blocks that make everything up. So the atoms are typically on the periodic table. That's where you're going to find a lot of those. And I like to imagine these as little bitty Legos. That's what I have in my head, at least. So when you buy a Lego kit, you get all of these like random pieces and parts that are all off on their own. They're all looking at their own shape, their own color, whatever the case is. And then when you get the Lego kits, you can actually take these Legos and you can build them in different ways. For the most part, that's the old school Legos. Like, that's when I grew up, right? They just gave you a mixture of Legos and they were like, you go build whatever you want to build. And they were super cheap and everybody had them. And now you're looking at $200 for a Lego kit that just has 30 pieces. I mean, it seems like that's what it is anyway. Either way, these are building blocks. They are in the kit and you have access to them. And yeah, you can use those to build what's in the picture. But at the same time, old school Legos, you were able to build whatever you wanted to build out of them. It didn't really matter. So the atoms to me are like Legos, and the Legos are going to come together and they're going to connect. And when they connect, we make something that we call molecules. Now, these molecules really are larger and they make everything up. And this is where diversity comes into the laboratory environment. There are tons and tons and tons and tons and tons of different types of molecules that are out there that I would encounter every single day. And all of these molecules are made up of these atoms, and these atoms are coming from a periodic table. All right, so the periodic table looks kind of like this, right? You maybe have seen this before. If not, no big deal. We're not going to go crazy with it, and we're just going to skim the surface when we begin to talk about these intermolecular and intramolecular forces, or AKA glue, that holds these things together. All right, so these are my Legos. This is what I'm going to be picking from. And Mother Nature has decided to go through and take some of these Legos and we make a molecule, and then and we make another molecule, and we make another molecule. Yay! We get millions of molecules, I guess, that come from these little Lego kits. And we've got to talk about the glue that holds these molecules together. So when these atoms begin to assemble, Avengers, assemble, right? I mean, okay, so when these atoms begin to assemble, they assemble to make different molecules, and just the difference of one little Lego, one little atom, can make or break a completely different molecule. All right, so let me give you an example here. Atoms from the periodic table. All right, we have hydrogen and we have oxygen. These are listed on the table. You will see H on the periodic table. You will see O on the periodic table. H is for hydrogen. O is for oxygen. Okay, these are different Legos. They might be different colors. They might be different sizes. They might be different shapes, but they are the building blocks to make things with. All right, so we could, at some point in time, be like, hey, I want 2 of the hydrogen Legos and 1 of the oxygen Legos, and all of a sudden, I get water. Yay, H2O, and we know that we have to have water in order to live. Okay, so this is a molecule. That molecule is made up of hydrogen atoms and oxygen atoms. Well, at the same time, I have this Lego kit, and I might get creative, and I'm going to go through it. I'm going to go, you know what? I'm going to connect these Legos in a different way, and I'm going to use more than what I used just now to make H2O, and I'm going to take hydrogen and 2 of those, and I'm going to take oxygen and make 2 of those. And guess what? That is not water anymore, because water is H2O, not H2O2. H2O2 is hydrogen peroxide that you buy in the store in a brown bottle that you put on a cut, and it begins to fizz and bubble, and you kind of sit there and watch it do its thing, and it doesn't really burn most of the time, which makes it even great. So this is something different. It is a different molecule because it's made up of the same atoms, but it's a different number of atoms that have made it up. So in definition, it is different. So we get Lego kits that have Legos on the inside, and of course they are meant to build things, but we can take these and we can be very creative, and we can get different things out of those Legos. And this is the way Mother Nature makes these molecules that we need in order to basically live and function on a daily basis. All right, so everything I come in contact with has molecules in it, and those molecules are made up of atoms, and those atoms come from the periodic table. All right, well, let's talk a little bit more about the atom before we go further. The atoms have what we call subatomic particles. All right, so subatomic. That sounds special, but it's really not. Sub means below. That's what that really represents, right? So we are talking about below the atomic level. That is what we are trying to discuss here. All right, so subatomic, below atom, there are 3 things in the subatomic particle area, and that's something that makes the atoms up. We've got to make the Lego, right? So what makes the Lego in the first place? Well, we can talk about something called protons, and we can talk something about electrons, and we can talk about something called neutrons. So protons, electrons, and neutrons. That's P-R-O, protons. T-O-N-S. I know it's chicken scratch. I get excited and I begin to write sloppy. So that's my fault. I'm sorry. And what on earth is this? All right. So N-E-U-T-R-O-N-S. Neutrons and electrons. Protons, we have an abbreviation that is P positive. And electrons, we have an abbreviation that is E minus. And neutrons, we have an abbreviation that is N. So protons, we have a positive charge up here at the very top, and that's because protons carry a positive charge. And neutrons have no charge at all. They're neutral, which is why we call them neutron. So some people write a 0 up here at the top, And some people don't. I mean, that's really up to you. I don't care what you do. But if you want to write a 0 up there, great. Do it. Makes you happy. Go for it. I know what you mean. But a lot of people are just like, why bother? It's neutron. There's no charge. So why even take the time to write a 0? Just leave it off. People know what you mean. And then the E has a negative up here at the very top, because electrons carry a negative charge. So this is going to become very important when we begin to talk about how things organize and how things come together and the behavior of the atoms at a certain point. But charges, I'm keeping it in your mind right now because charges are also coming around because it is glue that begins to hold things together. All right, so subatomic particles make the atoms. And different atoms, like hydrogen and like oxygen, have different number of protons, electrons, and neutrons. That's why they're different. That's why their colors are different. That's why they're bigger. That's why they're smaller. That's why they're a different shape. I mean, this, again, goes all the way back to the building blocks of life. And this is the Legos that we use in order to make the things that we need. So hydrogen has a different number of protons, electrons, and neutrons that make it hydrogen. Oxygen is an atom. It has different numbers of protons, electrons, and neutrons from everything else. That's why it makes it an oxygen atom. And those atoms come together and make new things. And those new things are molecules. So that's how all of this is connected at the basics of the basic level. And that is the difference between the atom definition and the molecule definition. Atoms are the simplest building blocks, and they make molecules which are a little bit bigger. So again, hydrogen, atom. Oxygen, atom. Water is hydrogen and oxygen coming together. That's a molecule. Peroxide, hydrogen and oxygen coming together. That's a molecule. All right, so when we have H2O or H2O2, the question is glue, right? What keeps these things together? Because at a certain point, they had to come together, and a certain point, well, when they did come together, they're staying together. So why aren't they just separating? Why aren't they just going back to the atoms again? Why are not they just breaking down? These are questions that we have to answer in this lecture before we go and talk about physical properties and physical tests that we can do on these molecules that are going to be given to us maybe in a lab environment or that we have to analyze in some form or fashion. All right, so with that said, what kind of glue holds molecules together? Well, there's two major intramolecular forces that we need to talk about. All right, so let me say intra. There we go. All right, so intramolecular. Intra basically means within. That is what that represents. So we are talking about a molecule that has come together, and that molecule has glue that keeps it together. And that glue is going to be two different types. And it's either going to be something that we call, number one, covalent, or number two, ionic. It's going to be one or the other. And we've got to figure out a lot of times, okay, what is the glue that's present? Because that will help me to determine what I need to do later on as far as testing goes. So with covalent bonding, if you look at the definition, it says bonds between two nonmetals, ooh, and they share electrons. That's kind of boring. And then ionic bonding says bonds between two charged atoms, and they transfer electrons. All right, so there are differences between the glue inside of a molecule, and you're either going to label it as a covalent glue or an ionic glue, aka bonding. So how do I know? Well, these definitions say, okay, well, most of the time they're two nonmetals, and if they're nonmetals all the way across the board, it's covalent. And then ionic says between two charged ions. All right, well, that basically means a metal and a non-metal. That's what we're looking for there, because those are going to create charges, and those charges will become the glue that will hold those two things together. So we got to kind of delve a little bit deeper into this in a way, And then I also see the word share and transfer. Oh, how sweet. Share and transfer. I'm going to share what I have with you, but then I'm going to transfer what I have with you. Which one do you want? What are the atoms doing? How do we know what the atoms are doing? We're not there. We can't ask them. Okay, well, there is an easy way to predict these types of things, and that's based on the position on the periodic table. All right, so here is a covalent bond. Oh, yay, how sweet. Up here in the top left, we see fluoride and we see fluoride. And look, oh, they're locking arms and they're skipping and they're smiling and they're having a great day at the mall. So they go shopping together and they talk about their day and they talk about their crushes while they're in school. And then they're sitting on the bench and they begin to talk even more and gossip about everybody that they go to school with. And today's environment, they're probably doing that on their telephone while they're sitting side by side on the bench, because that's what goes on. Instead of talking to each other, they'll text each other even when they're nearby looking at each other. Back in my day, we actually were social before social media came around, and we actually went out and we actually did stuff together and we actually talked to each other and didn't become a weird, awkward person in today's society. So these are having a great old time. Great evening on a Friday, Saturday night. Down here at the very bottom, yay! We get an oxygen here and an oxygen there. And they've went to the park and they're like, hey, look at us. We're playing on a playground, when kids actually went outside instead of stayed in their houses, in their rooms, locked away, playing the PlayStation or the Xbox or the Nintendo or whatever they're playing today. I don't know. But either way, yay! We're sharing an experience together. That's what this covalent bond is. So they're going out together. They are experiencing something together. They're sharing that experience, but they're not necessarily transferring anything. I mean, this person has paid their own way and that person has paid their own way. This person paid their own way to get to the park. That person paid their own way to get to the park. And, you know, they're not making an investment into each other. So they are simply sharing the experience that they have. And here is maybe like just a friend that's taken two little kids out to go to the movies. Yay! Okay, well, whatever. This is like a role model or somebody that they're looking up to. And they're like, you know what? I think we'll go to the movies. If your mom and dad don't want to take you to the movies, I'll do it. I'm a family friend. It's no big deal. Nothing weird. So I'm going to take you to the movies, but they're going to give you the money in order to watch the movie. I'll take you there and we'll share the experience together, but I'm not buying you soda. I'm not buying you popcorn. I'm not buying your ticket. That's the responsibility of your mommy and your daddy. Okay, and they're like, yay, 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 we gotta go, we gotta go. And then they'll go next week and brag about what they saw at the movies. So it is a experience that is shared. Nothing is getting transferred. That is the definition of a covalent bond. Well, in opposite of that is an ionic bond, and an ionic bond is like, hubba, hubba, baby. I mean, that's kind of what's going on here. So these two things go out, and these two things do share an experience, but there is a transfer of something that is happening. Now, you use your imagination on what's getting transferred here. So at the end result of this, it could be little salt babies that are beginning to get formed, but a transfer is taking place from one to the other. So what normally goes on is that, let's keep this clean. Let's say sodium and chloride go out onto a date, and they go to a restaurant, and they sit down on their very first date, and they madly go, hubba, hubba, hubba. All right, so if they do that, then what's happening is that sodium at the end of the night is going to say, hey, you know, I think I'm going to give you some money. Okay, again, I said keep it clean. But sodium's going to say, chloride, you know, I think I'm going to give you some money tonight. So it takes out some cash out of its pocket and it gives chloride some money. And sodium madly falls in love because chloride took its money. And chloride madly falls in love because sodium gave it money. And from that moment on, it is like set in stone. Hey, baby, that's what's going on here. So they have formed a relationship, and that relationship is based off of a transfer of something. That is what's happening in this type of bond. It is another type of glue that keeps molecules together. All right, so I told you that in definition, if you have to predict it, you use this idea of a metal or a non-metal. What does that even mean? All right, so here we find a periodic chart, and this periodic chart has what I like to call a staircase. All right, so I'm going to draw a staircase down the periodic table that looks like this. All right, so it starts at number 5, which is this after the valley. I call this the valley. After the valley, whoop, it goes back up. So here is atomic number 5. And that atomic number 5 begins our staircase. So down, over, down, over, down, over, down, over, down, over. All right, so that is a dividing line. It's a fence. And that fence on this side of the periodic chart are non-metals. And on the left-hand side of that staircase, these are the metals of the periodic table. All right, so by definition, we now know, okay, yeah, we can talk about sharing, and then we can talk about hubba, transfer of something, but we can also talk about positions on the periodic chart. So sodium and chloride come together. Sodium is a Lego. Sodium's an atom. Chloride is also an atom. It comes from the periodic chart. So if I go to the periodic chart, here is sodium, and sodium is to the left of that staircase, so metal, and I can stop right there. Absolutely. I can just stop. I don't need to know any more information. Sodium is a metal, and if I only have two choices, covalent or ionic, automatically, ta-da, this thing is going to be ionic. Whatever it comes with it, it's going to be ionic. And the reason is because sodium is a metal, and that is a requirement for an ionic bond. Covalent bonds do not have metals. It's all nonmetals all the way across the board. So there's sodium. It's to the left. It's a metal. Here is chloride at number 17. That is a nonmetal. That's to the right-hand side. So when sodium and chloride come together and hubba, there's glue that keeps them together, and that glue is a type of bonding. That bonding is an intramolecular force, and that type of intramolecular force is ionic bonding. All right, well, let's take a look at something like CO2, carbon dioxide. That's the stuff that comes out of your mouth. It's been coming out of my mouth for the past 22 minutes. A lot of it, I might add. So the CO2, if I look on the periodic chart, there is my carbon. Oh, that's a nonmetal. It's to the right of the periodic chart. Here's the oxygen. Oh, that's to the right of the step. Okay, it's a nonmetal. So if carbon's a nonmetal and oxygen's a nonmetal, guess what? They are going to see each other, and those two Lego pieces will be like, hey, let's hang out. What do you want to do this weekend? Talk about boys or girls? And they're like, yeah, sure, let's do it. So they go out, they have an experience together, they enjoy each other's time while they're together, but at no point in time is anything getting transferred from one to the other. They are simply sharing the experiences and sharing the idea of going out and being just simply together. That is the glue that's holding them together. So out of the two choices, if I look between covalent and ionic bonding, what I'm going to determine is that ionic bonding is going to be a little bit stronger. It's going to be a little bit harder to pull those apart because full-blown charges are actually getting formed here. Positives and negatives. One is losing the dollars and the other one is gaining the dollars. So that transfer that is beginning to happen is taking place. And that transfer, because it's making full-blown charges here, it's harder to rip that relationship apart. It's harder to break them up. Because at this point, after the first date, they're probably already married and they're probably going to have babies next week. I mean, that's kind of the relationship that's happening here in the ionic bonding / glue that keeps these molecules together. Covalent bonding, it's easier to rip those apart. right? The only thing that you got to do is go to school the next day and go up to one of those in the covalent bonding and be like, do you know what so-and-so did with your boyfriend or girlfriend yesterday? Let me tell you what so-and-so told me. And that's all you got to do. You plant the seed, and then you just sit and wait for the little plant to grow. That's what's happening here with covalent bonds. And then sooner or later, that covalent atom is going to look at the other covalent atom and go, I hate you. I never want to hang out with you again. I'm going to go to the principal and I'm going to tell everybody that I know what a piece of beep that you are. I hope you that's kind of the relationship that it is. Very easy to rip those apart. Of course it is in a laboratory environment. The one thing I want you to keep in mind, though, is our little exception, and we have a little exception here, and that exception is something that we call NH4. You know, there's always exceptions. That's just the thing. There's always exceptions with this stuff. All right, so with NH4, if you look at NH4, and it is bonded to something else. All right, so we're talking about NH4, and then we could have like chlorine off the side or something else. Okay. I'm going to look at this, and I'm going to use the definition that Trace just told me. Nitrogen. Oh, okay, let me pull out the periodic table. All right, so here's the periodic table. Nitrogen is right there. Oh, number 7. Woohoo! That's a nonmetal. NH. H is here. Woo! It's a nonmetal. Wait, you told me everything to the right. Well, yeah, but hydrogen is an exception. Hydrogen, it's on the left-hand side, but it's always regarded as a non-metal every single time. It's one of the ones, or one of the few, that is regarded as a non-metal that is only on the left-hand side. So that's not the exception I'm talking about. Anytime you see hydrogen, you treat it as a non-metal. It is part of the non-metal family, even though it's to the left. What you will find out, that we will talk about many times throughout the program, is that poor little hydrogen has nowhere to go, has no home. Where does it go? It doesn't really go to the left. It doesn't really go to the right. It doesn't fit in the column that we put it in. It has nothing to do with any of them, and it's like, oh no, I'm all alone on this little island, and nobody loves me, and I don't really fit in with anybody. Oh, hydrogen. All right, so hydrogen is, though, in this time, and all the times, classified as a non-metal. Again, it's in an odd place, but that's where it is. All right, so nitrogen's a non-metal, hydrogen's a non-metal, and then let's say it's chloride that's there. Okay, chloride. There it is, number 17. So all of these are non-metals. And you will look at this example and you'll say, oh, well, look, in hydrogen or nitrogen, non-metal, hydrogen, non-metal, chloride, non-metal. And then you're going to write down this thing is a covalent bond. Alert, 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 alert. No, it's not. This is why whenever we see NH4, there's an odd little thing that happens. And NH4, when it's together like this, you need to regard that as a metal. I know. It's just the way stuff is sometimes. There's exceptions to everything, and this is one of those exceptions that we do see very often. And whenever I see the NH4, and that NH4 is called ammonium, that ammonium is going to be treated as a metal, and that is going to be a metal paired with chloride, which is a non-metal. So therefore, NH4Cl is an ionic bond that we have to talk about. So that's one of the few exceptions that we're going to see in the very beginning. It's really the only one that we focus on, not a big deal. And that is why you're going to see this as typically 3 examples that I give you. 2 we've already talked about, the third one we just did. So again, sodium is a metal and chloride is a non-metal. So therefore, metal and non-metal make ionic bonding. A transfer happens, which is the glue that keeps those things together. Carbon is a non-metal. Oxygen is a non-metal. Therefore, it is covalent glue, covalent bonding, that holds that molecule together. And then NH4Cl. NH4 has to be treated as a group, and that's the strange one. It is a metal classification. and Cl is chloride. So metal and non-metal make an ionic compound in this case, and that ionic compound is a transfer of electrons, and that transfer is the glue that holds these molecules together. All right? So sodium chloride and ammonium chloride in these examples are transferring electrons, and carbon dioxide, the stuff that you're breathing out, that is covalent, which means they're sharing electrons when they go out together and enjoy their time together. Out of these two, or three, out of these three, the carbon dioxide is going to be the easiest to break apart. And the reason is because it's covalent bonding and not ionic bonding that's at play. All right, so that will sum up what we call intramolecular forces. And these are bonds within a molecule that keep that molecule together. And we've got two major choices here, ionic and covalent, and now you know the difference. All right, so in the next video, we're going to talk about more glue. And this time, we're going to venture outside of the molecule and talk about the glue that basically holds many molecules together, because we're getting bigger and bigger and bigger. So that's what's coming up next. Enjoy the show. Come back and see me. I'll be waiting. Go take a potty break. I know you love this stuff. And I love making a fool out of myself and giving you all of the little voiceovers and sound effects that I could come up with. You know, I mean, this might be a new job market for me.